Alright, in this video we'll spend a couple minutes looking at AP quiz number 3. So this is based on the set of multiple choice questions that I'd given you to look at for last week. And in problem number 1 here, we're told that the position of a particle moving along the x-axis at any time t is going to be given by this formula, negative 2t squared plus 3. We want to determine what the average velocity is for that particle on the interval from 1 up to 3. Now, early on in chapter 2, we said that this idea, the slope of a secant line, this idea, average velocity, or generally an average rate of change, all of these ideas are tied to the same exact formula. And that formula is one that you've been using variations of for 3, 4, 5 years at this point, and it's this regular old slope formula, y2 minus y1 over x2 minus x1. So if it says an instantaneous velocity or an instantaneous rate of change or the slope of a tangent line, that's when we're going to need to do something with derivatives. But if it says average velocity, average rate of change, we're going to use our regular old slope formula. More specifically, for an average velocity, we're going to do change in position divided by a change in time. Okay? So what you can use this formula to do right here is you can determine the position of the object on the x-axis at t equals 1. You can determine the position of the object on the x-axis at t equals 3. So its position at 1 is going to be, so here's the time, and the position is going to be negative 2 times 1 squared plus 3, and if you simplify that, that would be the point 1 comma, negative 2 plus 3, 1 comma 1. And then at 3, we'd have 3 for the x value, or the t value, I guess in this case, comma, the position value would be negative 2 times 3 squared, which would be 9, plus 3. So that'd be negative 18 plus 3, which would leave us with 3 comma, negative 15. So we just want to use these 2 points to compute a slope between to find our average velocity. Change in the dependent variable divided by change in the independent variable. So we're going to have difference in y values or position values divided by the corresponding difference in t values, 3 and 1, and we're going to be looking at negative 16 over 2 or negative 8 for that average velocity. And the average velocity, if you knew that position was measured in feet from 0 on the x-axis and t was measured in seconds, this would be feet per second if it was miles an hour, miles per hour, or whatever the units of position and time are. Here they weren't really specified. But average velocity, regular slope formula, change in the dependent variable divided by change in time. The next 3 questions here, we're all asking you to draw graphs that served as counterexamples for each of these claims. So I made 3 claims here, and neither of these claims are true. The first claim is that all continuous graphs are differentiable. So if I'm trying to draw a graph that serves as a counterexample for this claim, I'd better be able to draw a continuous graph that is not differentiable. So a continuous graph can't have any holes or jumps or asymptotes or anything like that, and it has to have a point on it where the slope of the tangent line is undefined or where the derivative is undefined. Remember, differentiable just means the slope of the tangent line is defined or the derivative is defined. Easiest way to do this, in my opinion, would be to draw an absolute value graph. This is not differentiable at the cusp. The slope changes instantly from a negative to a positive. It doesn't gradually cross all values in between. This graph is not differentiable at the cusp. Another way that you could have drawn a continuous graph, right? No holes, no jumps, nothing like that. Another way you could have drawn a continuous graph that was not differentiable is if you would have drawn something that has a vertical tangent line on it. So we maybe looked at 1 or 2 in the book that looked like this. Like right here, and I was trying to do this at 0, 0, and then it happened a little bit to the right of 0, 0. We have a vertical tangent line, and we're not going to be differentiable at a place where we have a vertical tangent line. So a couple different options there. If you drew a graph that was not continuous, there's no way it could have been a counterexample for this. And that's what happened to a lot of people. People were drawing graphs with holes poked out, piecewise graphs with jump discontinuities. It had to be continuous and not differentiable to be a counterexample to this claim. If you look at part B of this, the limit as x approaches 2 on f of x is 3, then f of x is continuous at 2. So I want to make sure I draw something where this definitely happens, but it's not continuous. So it has to be a counterexample to this claim. And I'm going to start with a point on my graph at 2, 3. I'm not going to put a closed circle there, but as long as I approach this point from both sides, I'm approaching that y value from the left, I'm approaching that y value from the right, so my limit as I approach 2 is definitely 3. If I don't fill this hole in, my graph is definitely discontinuous. It's not continuous at 2. So this would be a graph that serves as a counterexample to this claim. I can actually use the same graph down below here. I've said, again, the limit as x approaches 2 on my graph is 3, then f of x has to be defined at 2. Well, check out this graph. The limit as I approach 2 is definitely this same y value, still 3, but my function is not defined at 2. Now if I put a point up here, it would still serve as a counterexample for claim B, but it wouldn't be a counterexample for claim C. Okay, so this graph can actually double for both of these.